Okay, so let's consider a ballistic pendulum example that shows how you can use conservation of momentum and conservation of mechanical energy all in the same problem. Here's the situation where we have a bullet, maybe something that's fired at an incredibly high speed. We have a hard way of measuring its speed. Back in the old days anyway, they had a hard time with this when they were first working with guns and ballistics coming from guns. How to measure those speeds accurately was difficult. So here we can use conservation of momentum and conservation of mechanical energy to work through this problem and figure out how fast this bullet comes in and strikes this block. So the basic idea of a ballistic pendulum is that you have a high-speed object coming in, colliding perfectly inelastically with a pendulum, in this case, suspended by some strings, a certain length L from this pivot. And when it collides perfectly inelastically, transfers its momentum to this entire system. Over here we have the system moving shortly after the collision. It's going to move with the same momentum as the bullet moved, because momentum is conserved during that collision. We do have a big loss of kinetic energy, which we will go through and show you how to calculate that, but momentum is certainly conserved since all forces are internal. After the collision occurs, and we do lose a significant amount of kinetic energy, whatever kinetic energy remains gets transferred into gravitational potential energy here. And so we can sort of look at how high this thing raises up above its equilibrium position after the collision. It rises up and transfers all of its kinetic energy to gravitational potential energy. We can work backwards through this to figure out what the speed of that bullet is. And this is how we would do it. Let's say that I have a bullet that has a mass of 50 grams. And it's coming in at some velocity that I don't know. Let's say that's the velocity of the bullet. It strikes this pendulum. Let's say that mass is 6.5 kilograms. So it's quite a bit more massive than the bullet. And let's say that it's suspended by a pendulum with a length of 2.50 meters is the overall length. When the bullet comes in, embeds itself into that block, the entire system moves, and let's say that it makes an angle of let's say 21 degrees with the vertical once it reaches its maximum height. What we want to do here is sort of work backwards, as I was saying, to figure out the speed of that bullet. Now what I'd like to do is I'd like to start with looking at this from an energy perspective. At this point it has all gravitational potential energy. Prior to this it had all kinetic energy, and that's after the collision. So this would just be a conservation of mechanical energy problem where K initial would go to U final. And again, we've looked at examples like that before. Now that's conservation of mechanical energy. Over here, we're going to use conservation of momentum, which essentially says that the momentum of the system beforehand equaled the momentum of the system afterwards. In this case, the momentum of the system beforehand was just the bullet moving. The momentum of the system afterwards was the actual block and bullet moving with a different speed, but with the same momentum. So let's go ahead and show you how we can calculate this given the information that I gave you here. So first thing I'm going to use is I'm going to use conservation of mechanical energy to figure out the speed after the collision. So the way that I'll do that is I'll just start with Ki is equal to U final. And in this case it's 1/2 m. I'm going to put down v after the collision squared. So that's the velocity that it has here. This says v prime. I'm just going to call it VAC. Now that's going to end up going to m times g times delta h. And that delta h is just how high it rises right over here. I'd like to be able to calculate that. By the way, this m is actually the total mass, so I'm going to put m sub t here. It's both objects moving. Big M plus little m, so I'm just going to change that to an m sub t down here. Let's go ahead and find delta h. Now delta h can actually be found by taking this triangle. If I think of this as a certain length, let's call that 2.5 meters. And this length is as well as 2.5 meters. That's this entire length here. What I can do is I can find this distance by using a little bit of trigonometry. That distance h is actually just 2.5 minus 2.5 cosine of 21 degrees. And if you go through that math there, you'll be able to figure out how we get to that. The 2.5 cosine 21 is just this length right here. That's 2.5 cosine 21. And when I subtract that from 2.5, I would get h. So we can go ahead and calculate what that value is. And that turns out to be about 0.166 meters. So again, just I'm disregarding significant figures at this point, but that's delta H. Now I would like to go ahead and figure out what the velocity after the collision was. So you can see that the mass cancels out there, and VAC, the velocity that the entire system moved with after that collision, is our typical 2g delta H, the square root of that. And I'm just going to go ahead and plug those numbers in. I'm not going to write those all here, but you get the idea. And that velocity after the collision is about 1.80 meters per second. And again, just using conservation of energy principles. Now this becomes the input, if you will, to the next portion, which is using P initial is equal to P final. So we're using two conservation laws, one for mechanical energy conservation, which occurs after the collision, which happens after the collision occurs. Conservation of momentum occurs during the collision. So we can go ahead and use that principle now too. The mass of the bullet coming in times the velocity of the bullet prior to the collision is equal to the combined mass, which would be the total mass of the block and the bullet moving with that velocity that we said it had after the collision. So that was this value right here. Now since I'm looking for the velocity of the bullet, you just go ahead and solve this for the velocity of the bullet. And when this is actually pretty straightforward at this point now. I just take that value that we had up top here, that's 6.55 kilograms. That's the total mass that was that's moving after the bullet collided. The velocity that it had after the collision is 1.8 meters per second. And then I'm going to go ahead and divide that by the mass of the bullet. And when I do that, I see that I get a speed of about 236 meters per second. So there's a way for us to calculate the velocity of a fairly high moving projectile by using momentum transfer and then mechanical energy conservation. Now what I would like to do is I'd like to determine kinetic energy loss. The kinetic energy initial is just 1/2 the mass of the bullet times the velocity of the bullet coming in squared. When you plug in those numbers, you're going to see that the bullet actually had about 1392 joules of kinetic energy. A lot of energy, a lot of capacity to do work. Now, the kinetic energy afterwards is the kinetic energy that the bullet and the block had right after the collision. Well, it had a much greater mass. That mass is about 6.55 kilograms, but it was moving at a much slower speed. And so it had a tremendous change in speed there. It came out of that collision with 1.80 meters per second. And I'm going to go ahead and square that term as well. And when I do that, I see that I have about 10.6 joules remaining. So where did all that extra energy go? Well, a lot of it went into changing the shape of that bullet, digging a hole, if you will, into that block of wood. A tremendous amount of heat built up. When I look at the total change in kinetic energy, what I get is about a negative 1381. And so a lot of energy went into other forms here. And again, that's evidence of all the destruction that you see, a lot of the sound that you hear, the heat that's generated, a tremendous amount of energy. That's the example for you. Hopefully that helps you understand it. And then there will be a few more problems for you to try on your own.